Hello and welcome to the Oracle CloudWord 2023. This session introduces you to new spatial features in the Oracle database version 23 and related tools. My name is Karin Patenga. I'm a product manager with the Oracle Spatial and Graph development team. And since I'm based in Germany, I focus on customers and partners in Europe, Middle East, and Africa. Location data is ubiquitous. You find it everywhere and everybody uses it intentionally or unintentionally. Oracle's primary goal in developing database products and services is to provide you with an easy-to-use platform that intelligently manages, processes, and analyzes any type of data and data processing workflows. We invest a lot in simplifying the development of Oracle database-centric applications using zero, low-code, or any code application development frameworks and tools. So, spatial data maintained in the Oracle database can be seamlessly integrated and used by an application along with any other data such as relational, document-centric, streaming data, graphs, or blockchains. Since our first support for Oracle Spatial in Oracle Database version 3, we've seen hundreds of new spatial features and functions built into any new database version. Every Oracle Database edition and service provides these features, known as Oracle Spatial. One focus of version 23 was to simplify creating and using the most common spatial data type, stereogeometry, that stores spatial data as geometries, or for that matter, points, lines, polygons, and combinations of them. Points, representing real locations on Earth, are often expressed as pairs of coordinate values. Therefore, we have made it easier to create stereogeometry objects directly from coordinate values. Besides spatial features built into the Oracle database, we additionally provide tools to load, validate, enrich, analyze, and visualize spatial data. One such tool is Oracle Spatial Studio, a self-service web application for everybody who seeks a zero-code environment to use spatial data in projects. For those who use REST interfaces to either access, share, or maintain spatial data, there is now a REST API to work with spatial data available as raster data. Those can be satellite or area images or gridded data like weather data. As part of our autonomous database service, we've introduced a simple-to-use PureSQL API to enrich address data with their coordinate values. In spatial data, we have enhanced the integration of background maps that external web map services provide. Last, you can find new functions introduced to work with and analyze 3D data. Very often, 3D data is provided by laser scanners that create point data sets, also called point clouds, from scanned real-world objects. I will explain in more detail 3 new features in that area later. But let me start with more details about the new simplification features I mentioned first. You can see the SQL statement on the left side to create an stereogeometry object representing a point from a pair of given coordinate values. It replaces the longer statement that requires specifying 5 object type parameters. You can use the same SQL syntax to specify point geometries and spatial queries. This is what you see on the right side. SDO within distance here is one of the spatial proximity search functions. You've just seen how to create point geometries using their coordinate values. Now, you can still create geometries specifying all 5 parameters of the stereogeometry data type, but instead of numeric codes for the geometry type, which is the first parameter, and B, the ID of the coordinate reference system as a second parameter, you can now use human-readable constants such as SDO_polygon2D, SDO line storing 3D, or SDO_lonlat and SDO_webmercator. The latter are represent two widespread reference systems with the IDs 4326 and 3857. 4326 represents the World Geodetic System 1984, and 3857 is the projected coordinate system used for rendering maps in Google Maps or OpenStreetMap. Those of you who have dealt with SDO geometry data before are also familiar with the concept of spatial data, spatial metadata. Every column of type SDO geometry having a spatial index needs to be registered as SDO metadata. SDO is short for spatial data objects. To register an SDO geometry column, you need to insert a record into database user-specific updatable view named user_geom_metadata. In 23.c, this record is automatically created upon the creation of the spatial index. Now let's quickly run through the new features of Oracle Spatial Studio version 23.1. Spatial Studio is available for on-premises deployment as a download from the Oracle Technology Network and for deployments on the Oracle Cloud, either via the Oracle Cloud Marketplace or via a reference architecture named Build a Geospatial Platform on Oracle Autonomous Database, which deploys Spatial Studio along with an Oracle Autonomous Database. The first one of the new Spatial Studio features refers to the ability to publish projects created in Spatial Studio. You can now more easily embed your projects via their URLs in external web applications. Just copy the URL and use it, for instance, in your Aplex application, or display the project standalone outside of Spatial Studio in a browser of your choice. When embedded in Apex, make sure the published project is flagged public. Paste the URL in your Apex region and specify the iframe attributes as region settings. The blog post mentioned at the bottom of this slide summarizes this and the other new Spatial Studio features. It also points you to a video on YouTube presenting the features. In Spatial Studio 23.1, we have enhanced displaying information for overlapping data layers. Before, if map layers overlapped at a specific location, selecting your desired data point could be challenging without hiding the layers containing data at the same point. In 23.1, the info window displays now attributes for all overlapping map features. We also added support for importing CSV files and Access spreadsheets that contain a column with geometries expressed as so-called well-known texts or as GeoJSON. Both formats are very popular and standardize the representation of geometries. During the upload into Spatial Studio, the data is parsed and stored as SDO geometry objects in the Oracle database. In previous versions of Spatial Studio, you can already use external web map services as background maps. What we have done in 23.1 is to better use the metadata information of a service with regard to its service layers. A description of the web map service layers is provided when calling its Get Capabilities method. The National Oceanic and Atmospheric Administration, short NOAA, publishes historical and forecast weather data as WMS, which are used here in my example. We have also improved multilingual support in Spatial Studio 23.1. You can now select the language for labels and vector tile-based maps But please note that this functionality depends on the translation data provided by the data provider, for example, OpenStreetMap. In my screenshot, you can see the language support for French as an example. The example used in our blog post refers to Japanese. This concludes the new features that simplify the creation of spatial data. Let's move on with more developer-oriented new features. With 23C, we've introduced a REST API for raster data. It contains methods to access raster data, process raster data, including applying raster algebra functions for analysis, import or export of raster data, and create, manage, and access virtual mosaics created of a set of raster data objects. You find the REST API endpoints documented as part of our 23C documentation. Similar to the new features of Spatial Studio, our geocoding PL/SQL API is not a new feature of the Oracle Database version 23. Instead, it relates to the Autonomous Database Service and is exclusively available there. The geocoding API is explained in detail in the blog post mentioned down here on the slide. With a simple function call, you can perform forward or reverse geocoding. Forward geocoding converts addresses into either a collection of JSON documents containing one or more best matches, or an geometry object representing a point that contains the location of the best match. Reverse geocoding converts coordinates into their textual address information. Please note that you need to enable a database user to use the interface. This requires connecting as the admin user to the Autonomous Database instance and granting access to the database user using the function. If you are familiar with, or if you want to check Oracle Live Labs, our platform for step-by-step workshops and guidance, we provide a sprint there for this topic. Within 5 minutes, you learn how to enable a database user and how this user can geocode addresses in the Autonomous Database. Let's have a look at the last set of new 23C spatial features. These are related to typically massive three-dimensional point data sets. They are becoming more and more popular and available since they have huge potential in being used in data-driven applications. To date, our focus has been on data management, ingesting, storing, and querying point clouds or extracting information from point clouds. LiDAR data, as mentioned here on the slides, is short for light detection and ranging data, and it is a remote sensing technology that uses laser light to measure distances and to create precise 3D models of objects and environments. There are plenty of examples where LiDAR data can be useful. To name a few, let's start with autonomous vehicles. LiDAR plays a crucial role in enabling autonomous vehicles to perceive and navigate their surroundings accurately. LiDAR sensors mounted on those vehicles emit laser beams that bounce back after hitting objects, providing detailed 3D information about the surrounding environment. This data helps vehicles detect and classify objects such as other vehicles, traffic signs, pedestrians, and obstacles, allowing them to make informed decisions to ensure safe navigation. Environment mapping. LiDAR data is extensively used in environmental mapping applications. It can provide precise elevation measurements and create detailed topographic maps, making it valuable for studying terrain features, land cover application classifications, and vegetation analysis. LiDAR is particularly useful for monitoring coastal erosion, managing foreign forest resources, assessing flood risks, or studying changes in landforms over time. urban planning and infrastructure development. LiDAR data is highly beneficial in urban planning and infrastructure development projects. It enables accurate and detailed mapping of urban areas, including buildings, city furniture, roads, and utilities. LiDAR data can help urban planners assess the suitability of sites for construction, analyze traffic patterns, optimize transportation networks, and design efficient drainage systems. The high-resolution 3D models generated from LiDAR data assist in visualizing and simulating future urban developments, aiding in decision-making processes. I want to highlight 3 new features in this area. First, detecting changes in point clouds captured at different times. Second, the computation of vertical cross-sections to perform 2D measurements or analysis of 3D data. And the conversion of point data to meshes in order to represent 3D structures as objects for visualization. The POC function to calculate differences in point clouds is provided by a POC package called SDO_PC_package. And the function is called PC_difference. It compares 2 point clouds by identifying points within the first one with or without close neighbors in the second one. The result of this operation is a third point cloud. Running this kind of analysis helps you to detect damages after a natural disaster or the weekly progress on infrastructure development projects. The images of point clouds used here illustrate landscapes where the point cloud on the left side represents about 2/3 of the point cloud seen on the right side. So again, the point cloud on the left side represents a landscape. The point cloud in the middle represents about 2/3 of the point cloud on the left side. And the result of the difference operation is actually the remaining part of the first point cloud seen from the left side. Computing a cross-section of a 3D cloud in using a virtual 2D plane helps you in determining outlines of objects or with measurements inside point clouds. Such an operation is performed by using the POC function generate_cross_section_s_geoms. Its result is stored in 3 tables, one of the tables containing the point clouds, the 2D points on the input plane. The last of the new 3D features is provided using functions in the POC package SDO_tin_package. TIN is short for Triangulated Irregular Network. We've extended our TIN support to also include 3D meshes. A mesh can model a 3D triangulation of objects, including vertical surfaces, overhangs, and closed volumes, which are currently not supported by TINs. Although a thin better represents a sloping surface, 3D meshes can be used to model more complex landscapes, waterfalls, cliffs, or even buildings, cars, and others. And in contrast to the Delaney triangulation of a tin, a 3D mesh is generated from a point set based on the ball pivoting algorithm. What you see on the left side is a synthetically created 3D point cloud data set represented by 3 coordinate values x, y, and z stored in the columns val_d1 to val_3. The POC function create meshes, which you can see in the middle. takes the input data and stores the resulting mesh as a new 3D tin object in the destination table is also specified by the function parameters. This is what you can see in the middle. Visualizing a 3D mesh requires a format that 3D object viewers can interpret. Such a format is OBJ. We use the function clip_tin_into_object to generate an OBJ file from a 3D mesh. The result I can visualize using a 3D viewer. So the following short video illustrates the steps explained for 3D maps. Okay, so with this demo, I want to conclude the 23C What's New on Oculus Spatial tour. We keep developing and delivering spatial innovation for both on-premises and cloud deployments of the Orica database and related tools. We continue focusing on simplifying the development of location-enabled data-driven applications for any scale or criticality. And we encourage you to try Oracle Cloud Services to set up and run your own spatial data management platform. If you want to learn more about Oracle Spatial, please check out the links listed here. Thank you very much for your interest. If you want to provide feedback or have questions, feel free to email me.